Hello, hello, hello. Hello, everyone. Welcome. Uh, can't recognize any of the names, but hopefully some last year's Compass students here today. So we don't have a chat today, but we have a Q&A. So on the bottom, you can press Q&A, and if you have a question, just type it in, and I will answer the question. Or David. David is here to help us. He's one of our tutors. Hi, David. And yeah. So today is the first webinar for year 11, and the topic is ideal gases. I'm going to share my screen. And you should be able to see my screen. Okay, perfect. So I'm going to talk to you about what COMPOS is about. So if you are new to COMPOS, of course, and for you to understand how we work, and then yeah, and then some things. So yes, COMPOS was founded in 2021 by Professor Alexander Lvovsky. You'll get to meet him at the induction webinar, which will happen in a few months. So I think it's a launch webinar. It's called a launch webinar, and we'll tell you more about the program. So I'll just talk briefly. So we have different branches of COMPOS. We have the main program. The main program is when you need to pass your entrance test, and you get assigned a tutor. So you have the entrance test, which is the first assignment. So first assignment, and that's physics and maths, is your entrance test. We don't know the passing score, but historically it was 50%. Last year it was quite a bit higher than 50% because we were limited in the spaces. Now we have 1,000 places, so hopefully you won't get there won't be any limits and anyone can get in. So anyways, you need above 50% to pass, above 50%. So in both subjects, of course, the entrance test. Then we have you get assigned to tutor, and you have tutorials every week. Well, it's not every week. It's 3 weeks out of 4. Every week. Every week. You have 10 assignments. Oh no, sorry, you are year 11, so you have 6 assignments. One every 4 weeks, and you finish in around February, ends in February or early March. I don't exactly remember, but half term, February half term, roughly. Okay. Now you have the assignments are mandatory. These are mandatory. And to participate in COMPOS, you are expected to complete at least 75% of the assignments. So yes, mandatory. Ends in February. Tutorials are also mandatory. Yes, mandatory. So that it requires you. So this is 1.5 hours. That's the tutorial. Then you have 3 to 5 hours. That's your work. That is your homework. That's per week. And webinar is optional. This is a kind of commitment that you give to us that we expect you to work, well, between 4.5 and 6.5 hours every week if you want to be part of the main program. Okay, so that probably means, I don't know, less, well, whatever people do these days, less skateboarding or less dating. I don't know, whatever you do after school. So it is quite a big commitment. So be aware of that. The fruits of that commitment are of course great because our first cohort, 50% went to Oxbridge. Okay, so uh, so we think we give really good knowledge and really good skills in physics and maths, which are good that we can pass any other exam with flying colors. The follow along program, this is you only have assignments which are not mandatory. So you have the 6 assignments which are not mandatory, and you have the webinars. You don't have tutorials, unfortunately, but at the end, if you submit all the work, okay. Now, the follow along and yeah, 6 assignments which are not mandatory. Ooh. You have webinars, this is my webinar. You're free to attend. The webinar timetable is on our website. So that is here. Webinar, year 11 webinars timetable, and we are doing the first webinar, which is ideal gases. Okay, so we run until the 10th of March. Okay, 10th of March, so slightly more than I said. At the end, whether you do the main program or follow along, you will get a certificate. Now, it's important to understand that this certificate doesn't get you places, right? It doesn't give you, doesn't get you into Oxbridge, or doesn't get you, yeah, it's not that you have the certificate and you're more likely to get. What we give is the skills and knowledge that you need to pass entrance exams to any university. So, of course, there are multiple ways you can potentially get help from others or cheat your way through with, I don't know, so modern technology and everything. You'll probably get a certificate at the end, but then if you don't have the skills, that doesn't take you anywhere. The COMPOS certificate is useless on its own. Okay, useless on its own. Actually, it might play against you. So, for example, if you have a COMPOS certificate which says you've completed every single assignment and you had really good, and I don't know, somebody helped you with it, and then you went to a university interview and they asked you a physics question which you couldn't answer, that would really play against you, honestly. Like when I'm interviewing a person from like who bring me really good results, and then I ask them a simple question and they can't answer it, that looks really bad. Whereas when a person comes in and their skills correspond to their achievements, which is absolutely fine. Okay, so that's just a few things. Yeah, so our students are quite successful in getting into high-ranking universities, and a lot of them say that they wouldn't even think of going to Oxford if they didn't do Compos, and which is really some great feedback. We're not expecting to get 50% of our students into Oxbridge because Oxbridge doesn't have enough places, right? So if we have 1,000 students now, yeah, Oxbridge doesn't have 500 places on their physics course. Anyways, let's talk a little about, so problem one, it's not a real problem. It's using algebra in physics. Oh, I'm missing the question. Apologies. I'll have to copy the question. Just a second. I don't see any questions so far. You can ask me questions. It's in the. Oh, it's in the. It's on the screen. You should see it. Okay. Using algebra in physics, a bag of sand is dropped from the roof of a 30-meter building. But find how much the sand heats up when it hits the ground. This is not a it's a question unrelated to our topic today, but I just want to demonstrate how algebra is used. So you have a bag of sand and it falls from a building of height 30 meters. 30 meters. And as it falls, then it hits the ground. And it stops when it hits the ground, as bags of sand tend to stop when they hit something. So this is a conservation of energy question. And how, so at the top, the bag has gravitational potential energy. Gravitational potential energy. And at the bottom, it has no gravitational potential energy because it turns into thermal energy. Okay, so how would a typical GCSE student approach this, or the typical GCSE approach? You would try to calculate the gravitational potential energy. So you know the gravitational potential energy is mass times gravitational field times the height. And then you run into a problem because you don't have the mass of this bag of sand. So mass is unknown. So you can't calculate gravitational potential energy. So that's equal to mass times gravitational field, which is about 10, times the height, which is 30. So you kind of got stuck. Of course, there's way out of it. So this is with no algebra. And then the thermal energy, Q is equal to mass times the specific heat capacity times the change in temperature, which is, once again, you cannot calculate the change in temperature because, well, you don't know the energy and you don't know the mass. Okay. Yeah, specific heat capacity of sand, C is 800 joules per, oh no, it's 1600 joules per kilogram per degree Celsius. Is it? Well, let me double check. Specific of sand, 800, sorry. Yeah, that much, this is 800. It's not really important, but yes. Okay, so the COMPOS approach, or the algebraic approach. Physics problems are usually done with algebra. So what you do is you calculate gravitational potential energy. Gravitational potential energy is equal to mgh. H capital. And then the thermal energy, Q, is mc delta T. And because we know that the gravitational potential energy turns into thermal energy, there's a energy transfer from gravitational to thermal, you can equate them. You can say that mgh is equal to mc delta t. And we know the mass is the same. The mass is the mass of the bag of sand. So you can divide both sides by m. So you cancel the m's, and you get gh is equal to c delta t. And because we're looking for the change in temperature, we can divide both sides by c, and we get the change of temperature is gravitational field times height divided by c. And realistically, this is the answer we need. We don't mind if you I don't mind if you forget to put in the numbers. Okay, if you get the correct algebraic expression, that's what we need. That's that's the way most answers should be given. So can see there's no mass because mass cancelled. We don't need it, right? And then we can calculate. So put in the numbers. So putting in values, and you get change in temperature is gravitational field times height divided by c. We know that the gravitational field is 10 newtons per kilogram. Height is 30 meters. And then the specific heat capacity is 800 joules per kilogram per degree Celsius. Right, so kilograms cancel. Celsius goes on top, so that's 10 times 30 divided by 800. And that's going to be, and it's newtons meters degrees Celsius divided by joule. And Newton times meter, you will learn that it is a joule. So these cancel out, and you get 30 divided by, so that's 3/8 of a degree. So that's about 0.375 degrees Celsius. So yes, if you drop a bag of sand from 30 meters, it will increase the temperature by about 0.37. Okay, so there's a question. All right. Oh, yes, sorry. This you can you can always access this whiteboard. Let me open chat. All right, so I've typed the link in the chat. You can always have a look at this whiteboard. You can look at it at any time. Everything we do will be here. Okay. And, yes. Lovely. Okay, another example, and another example unrelated to our today's topic is a skydiver. A skydiver of mass m is falling at terminal velocity. Assuming that the coefficient of air resistance K is known, find the speed of the skydiver. The way air resistance works, air resistance is usually modeled as a constant. So let's say m multiplied by the speed, or it's equal to a k times v squared. So the difference is if you're going slow, air resistance is proportional to your speed. If you're going fast, it's proportional to your speed squared. Right. Oh, sorry. K. kv squared. Or kv squared if moving fast. Fast or slow is quite a relative question. So I would say a skydiver is fast. Basically, it depends on whether the the air flow around the object is turbulent or not, but that's not that important. We're going to say that the air resistance, we're going to choose this one. Okay, so what's going on? So we have a skydiver. The skydiver is falling through the air, and there are forces. So there's the gravitational force pulling the skydiver down, which is equal to mass times the gravitational field. And there's the air resistance. The air resistance is going up, which is kv squared, where k is a constant and v is your speed. And this is the air resistance. And this is the weight. Now, because the skydiver is falling at terminal speed, because speed is constant, the forces are balanced. Forces are balanced. Okay, so and if the forces are balanced, that means kv squared is equal to mass times gravity. And we're looking for the speed. So v squared, we divide both sides by k. We get v squared is mg divided by k. And we find that the speed, well, it's plus minus square root of mg over k, but of course it can't be negative. So v is square root of mg over k. And that is the answer that you give. So a typical answer at COMPOS will look like this. And a typical answer at university will look like this. So we're trying to teach physics similar to the way that it will be taught at university. So this is the answer. And then putting the numbers in, just the last thing. If it's a cosmetic thing, just to check whether it makes sense. So I could say that 10, 10, k is about 5, perhaps. 100 times 10,000 divided by, no, okay. Never mind. It's not important. It's not important what k is. Everything I'm trying to say is that give your answer as an algebraic expression, then put in the numbers, and separately you can write, I don't know, whatever, that's 55 meters a second. That's the typical speed for a skydiver. We don't know. But anyways, cool. All right, so now finally we get to the topic, that we've all come here for, which is the assignment on gases. So if you haven't seen the assignment, it's on our website. You get involved assignments, and it's here, year 11 physics assignment 1, ideal gases. Okay, so it's due the 5th of October, so you've got about a month and a half to do it. Okay, and yes. Right, so today I'm going to go through some questions which are very similar to the questions in the assignment. Some are not so much. And I'll start by introducing, well, the gas laws, Boyle's law, Charles's law, and Gay-Lussac's law, which is also known as the pressure law. So what on earth are we talking about? Well, gas has, the main 3 macroscopic parameters of the gas is the pressure, the temperature, and the volume. Let's have a look at this simulation. So this is an ideal gas and pressure. Okay, so this is an empty container which doesn't contain any gas. So you can see that the temperature is unknown. There's no such thing as temperature because there's nothing in it. The pressure is 0, and the volume, volume is the volume. We can measure the volume of the container, 15-ish, 15 something. It's not important. Okay, let's keep that. So the width of the container is proportional to the volume in this particular case if the container has a constant cross section. So let's ignore the word width, just use the word volume. So don't worry about volume. Volume 5, pressure 0. So let's add some gas. I've added some gas, and now you can see that the gas spreads out evenly throughout the container. The gas is made up of tiny atoms or molecules, depending on the gas. If it's helium, it's atoms. If it's oxygen, it's molecules, for example. And now we have a pressure inside the gas. So pressure is how the particles hit the walls. And when the particles hit the walls, they exert pressure on the wall. And this pressure can be registered with a manometer. The temperature of the gas, 27 degrees. And then there is the volume. So we can change the temperature by heating the gas. And that makes the particles move faster. So, and because the particles move faster, that also increases the pressure. So you can see that the pressure is doubled, roughly. We can change the volume. We can give the particles more space, and that reduces the pressure. Well, it reduces the pressure because the particles hit the walls less often. There's more spacing, so the particles hit the walls less frequently, so there's less force on the walls. The temperature can also change. On this model, it doesn't. But normally, if you compress a gas, the temperature also changes. But it doesn't do that. There are limitations to this simulation. Okay, so temperature is how fast the molecules are moving. Pressure is how hard they hit the walls. And volume is, well, the volume of the gas, of course. Right. Okay, and the gas laws deal with these three things. So the Boyle's law is the most famous law. Says that for a fixed amount of gas, or a fixed number of atoms, fixed number of atoms at a fixed temperature, increasing the volume causes the pressure to decrease. And we can verify that quite easily. So we can say, let's say the volume is 5, the pressure is 4,800. So volume is 5, the pressure is 4,800. If I increase the volume by a factor of 2, so 10, the pressure is 2,400, 10, 2,400. And if the volume is 15, then the pressure is 1,600. 600. And if I draw a graph of pressure versus volume, when the volume is 5, the volume is 10, and the volume is 15, the pressure is 1,600, 2,400, and 4,800. So you can see this nice curve. If I were to keep increasing the volume, the pressure would keep decreasing. And if I squeeze the gas, the pressure will go up. Okay. Now, Charles's law says that if you increase the volume for a fixed amount of gas at a fixed pressure, increasing its temperature will proportionally increase its volume. Okay, so let's test that. So we have the temperature and the volume. Okay, so how does that work? So I'm going to fix the pressure. So I'm going to put it somewhere here. And the temperature has to be in Kelvin. That's important. I'm going to cool it down to 200, let's say 200 Kelvin. Okay, volume is 5, pressure is 1,600. I'm going to keep the pressure fixed, about 1,600, let's assume. Okay. Okay. Pressure is 1,600 and it's fixed. And now look what happens if I heat up the gas. So at 200 Kelvin, the volume is 5. At 200, the volume is 5. Now, if I increase the temperature of the gas, let's say to 300, you see, to keep the pressure constant, the volume has increased to 7.5. How does that work? Well, you heat the gas expands. That's quite simple, right? Like, we know that. So 300, it's 7.5. And it is proportional. And if I keep increasing the temperature to 400, you can see it went to 10. 400 is 10. So you can definitely see that it is a linear relationship between the volume of the gas and the temperature. Now, there's a dotted line here. Because the reason is that because you cannot have a gas at 0 Kelvin. 0 Kelvin is unattainable. It's the lowest temperature that you could have, lowest temperature possible in the universe. It's called the absolute zero of temperatures. So 0 degrees Kelvin is minus 273.15 degrees Celsius. This is the lowest temperature that you can have. Okay, well, right. Next, we're going to quickly go through. We have temperature versus pressure. So the Gay-Lussac's law says that the pressure of a gas, the temperature of a gas, if you change the temperature of a gas, the pressure also changes. So let's check that. So we're going to keep the volume constant. So let's reduce the volume to, well, 6 is okay. 6 is okay. The volume is fixed. And I'm going to cool down the gas to 200 again. Okay, so 200 degrees, the pressure is 1,300. Temperature 200, 1,300. If I increase the temperature to 300, the pressure goes up to about 2,000, roughly. So 300 is 2,000. And if I keep increasing, 400. Okay. 2,600. So 400 is 2,600. Also, you can see that there is a linear relationship. If you double the temperature, it doubles the pressure. So the pressure versus temperature. And you can see that this is the Gay-Lussac's or the pressure law, which is, you will learn it as the pressure law in school. Yes. Cool. So when you combine these three laws together, so let's recall. So for the first one, P is proportional to 1 over V. And that also means that P is equal to K over V, which means that P times V is constant. For the second one, we have V is proportional to T, or in other words, V divided by T is constant. And for the third one, for the Gay-Lussac's law, so pressure is proportional to the volume, and that means pressure divided by volume is constant. And if you combine all these three laws, let's say you multiply, not really multiply them, but if you combine them, you get PV divided by T is constant. And this is the combined gas law. Combined gas law. So for the pressure times the volume divided by the temperature of a gas is a constant value. And that's very important. That's true for any for any for any for any fixed amount of gas. True. Or any fixed amount of gas of kill. Right. So I hope that makes sense. And the ideal gas equation looks like this. PV equals NKT, where P is the pressure, V is the volume, the pressure in pascals, volume in meters cubed, N is the number of molecules or atoms. K is the Boltzmann constant. And T is the temperature in Kelvin. If you don't know what Kelvin are, well, it's explained in our assignment, and you can also Google things. Temperature in Kelvin. Now, another ideal gas equation looks like this, the universal gas. So PV equals nRT. And this is obviously P is the pressure, volume. N is the number of moles of gas. One mole is 6.02 times 10 to the 23 molecules. So basically, it's the number of, sets of 6.02 times 10 to the 23 molecules. R is the universal gas constant, is 8.31. And I never remember the units. It's somebody knows the units. Joule, something more, something. Is the universal gas constant. And T is obviously the temperature in Kelvin. I don't know if you noticed, but these equations really don't take into account the type of gas you're using. The equation for oxygen and the equation for helium are identical. If you have the same number of oxygen atoms of oxygen, or you have the same number of atoms of helium at the same temperature in the same volume, the pressure would be the same. And let's investigate that. So let's say we have, let's say the blue ones is heavy gas. So let's say we have a volume of 10 and a temperature of 200. And the number of atoms is 100. 100. So 100 heavy atoms Okay, so 100 heavy atoms, and yeah, at a temperature of 200, pressure 776, and the volume is 10. Well, pressure is about 800. Yeah, it fluctuates, right? Obviously, it's 8. It jumps up and down around the 800 mark. Oh, now we have a. Let's remove the heavy gas and add light gas. So suppose it's helium. Now there's 100 atoms of light gas, and the temperature is, we need to lower the temperature to 200. And what do you see? With a different gas, which is lighter, if you have 100 atoms at a temperature of 200 Kelvin and a volume of 10, the pressure is exactly the same. So any gas, this equation is true for any gas, and it doesn't matter what gas you have. The pressure doesn't change. Even if the molecules are really, really heavy, like radon, it would behave the same way. Okay, is there any questions? The webinar timetable, you just you go on our website. Go on our website about Compos webinars, and this is the timetable. Okay. Perfect. All right, moving on. What is the density of air at room temperature? What is the mass of air in your room? So let's try to figure that out. The density of air. The density is mass divided by volume. What do we know about air? Well, air is made up of 75% nitrogen, N2, and the molar mass of nitrogen, molar mass, is 28 grams per mole, and 25% oxygen with a molar mass, it's not 25, it's something less than that, but it doesn't really matter. Molar mass of 32 grams per mole. So because there's 75% of nitrogen, the molar mass of air is closer to 28 than to 32. So the average molar mass is 29 grams per mole. This is the number that we're using. That 1 mole of oxygen is 29 grams. So molar mass is 29 grams per mole. So the molar mass is the mass of oxygen divided by the number of moles. Or in other words, the mass of the gas is the molar mass multiplied by N. Okay. So we can write the gas law, ideal gas law, PV equals nRT. And from here, N, well, the number of moles can be written as PV divided by RT. And so the density is mass divided by volume. And we know that the mass is the molar mass multiplied by the number of moles divided by the volume. And the number of moles is PV divided by RT. So it's the molar mass multiplied by the number of moles. So PV divided by RT and times V. V cancels the volume. So we have the molar mass times P, the pressure, divided by RT. Right. So we've solved the problem algebraically. And now we just need to put in the values to get an answer. So the molar mass of air is 29 grams per mole, which is the same as 0.029 kilograms per mole, because we have to do it in standard units. Pressure, atmospheric pressure is 100,000 pascals. That is something that we should know. It's 101 technically, but 101,000, but let's not worry about it. Universal gas constant is 8.31. I don't remember the units. Okay, I have to look it up. It's gas constant. Joules per mole per Kelvin. Okay. Joule per mole per Kelvin. All right. And finally, we got the temperature. Room temperature is about 20 degrees Celsius, which is 20 degrees Celsius, which is 293 Kelvin. So all I need is to put that in. So 0.029 kilograms per mole multiplied by the pressure is 100,000 pascals divided by the gas constant, 8.31 joule per mole per Kelvin, and multiplied by the temperature is 293 Kelvin. So Kelvin cancels. Yep. Per mole, so mole to the power minus 1 cancels. So you've got kilograms, pascals, joules. Joule is Newton times meter, as we already know. So 0.29. So that's 290 divided by 8.31 times 293. No, that's wrong. 2,900. Yes. And then we have kilogram, Pascal. Pascal is Newton per meter squared. This is joules, which is Newton meter. Yes, so Newtons cancel. And we get 2,900 divided by 8.31 divided by 293 is about 1.19 kilograms per cubic meter. This is the approximate density of air at room temperature. And finally, what's the mass of air in your room? So, my room. Well, of course, every room is different, but I know that this is about 2.3 meters height. This is about 3 meters, and this is 3 meters across. So my room, the volume of my room is 3 times 3 times 2.3, which is 3 times 3 times 2.3 is 20.7 cubic meters. The density is 1.19 kilograms per cubic meter. And I know that density is mass divided by volume. Therefore, the mass is density times volume, which is 1.19 kilograms per cubic meter multiplied by 20.7 meters cubed. Meters cancel out, times 1.19, which is 24.6 kilograms. So in my room, it's about 24.6 kilograms of air. Maybe the 0.6 is not very useful because, yeah. My volume is not that big. My volume is just about 70 liters. So it's about 0.07 cubic meters. That's my volume. So that's all right. 224.6 minus 0.07. Yeah. Oh, okay. Anyways, amazing. Okay, so yes, at COMPOS you can always round gravitational field strength to 10. In school for GCSE, yes, it is 10. For A level, it is 9.81, and they're quite strict with it, so please be wary. So I've answered the question. Cool. Problem 5. I like this one, and it's very similar. It's incredibly similar to, well, okay, not that similar, but it is on the similar to the one in the assignment with the Julius Caesar. Julius Caesar. Okay, take a deep breath. Your lungs will contain about 6 liters of air. The partial pressure of carbon dioxide in your lungs is about 4 kilopascals. What does that mean? That means if you remove all the other gases from your lungs and you leave just the carbon dioxide, and you manage to keep your lungs at the same volume, the pressure would be about 4 kilopascals. That's what partial pressure is. So if you have 800 kilopascals is the volume, or it's the pressure of this red gas. If you add 100 heavy atoms, you double the pressure. So you could say that the partial pressure of each gas is 800 kilopascal. Okay, if I were to leave only 50 heavy particles, the pressure would be 1,200. That means that the pressure of the red gas is 800 and the pressure of the blue gas is 400, which makes sense. If you double the number of atoms, you double the pressure. So if I remove the light particles completely and you leave just 100 heavy particles, it's 800 kilopascals. So if you have a mixture of a gas, the partial pressure depends on how many atoms of such and such gas you have. So in your lungs, you have about 4% carbon dioxide. That means because the pressure of atmospheric pressure is 100 kilopascals. The partial pressure of carbon dioxide is about 4 kilopascals. As you know from the course of biology, carbon dioxide is absorbed by the trees, by the leaves of the trees via photosynthesis. You know that, right? So carbon dioxide plus water plus sunlight make oxygen. But oxygen is O2. Carbon dioxide is CO2. So that C becomes part of the tree. So the tree grows because the tree absorbs carbon, right? Trees are made of carbon and they get that carbon from the air. And you exhale carbon dioxide, the tree absorbs carbon dioxide. So kind of the tree grows because you breathe onto it. Not, of course, that's a very small amount, but okay. There are 3 trillion trees in the world. I Googled that. I have not looked at references, but I'm assuming that is true. How many molecules of carbon dioxide do you provide for each tree? Of course, because yeah, you're providing carbon dioxide for the tree to grow, right? So the plants in my room, dead, unfortunately. I don't know why. Maybe not enough carbon dioxide. So right. So yes. So first of all, if we have a question like that, so we like questions like that in at COMPOS because you have to figure out a lot of things for yourself. Right, apologies. I had a blackout. Yes, the electricity went out. Uh, yes, am I audible? Yes, I had a blackout. Right, so are we still recording? Yes, we are still recording and okay. People are still here, which is good. Um, all right, so where was I? Oh, I need to share my screen. And cool. So if you have a question like that, well, it says how many molecules of carbon dioxide you provide for each tree. So obviously you want to know how many molecules of carbon dioxide you have in your lungs. Okay, so let's start writing things out. So we know that the volume is 6 liters. Volume is 6 liters. So this is 0.006 cubic meters. What else do we know? Well, we know the atmospheric pressure is 100 kilopascals or 10 to the power 5 pascals. Now, well, that's the pressure of the atmosphere. So we don't need that. 4 kilopascals, which is 4,000 pascals. PV. What else? Well, we can write the equation. PV equals NKT. Oh, well, we know the temperature. Temperature is about in your body is about 36, 37 degrees Celsius. Which is roughly to 310 minus 2, no, 37 plus 273. Oh, yes, 310 Kelvin. Oh, wow. So, yes, so you can actually uh, calculate the number of atoms. And we know that the Boltzmann constant or the Boltzmann constant 1.38, yes. Is that? Okay. Oh, so we can calculate the number of atoms. So it's PV divided by KT, which is pressure is 10 to the power 5 pascals times the volume, which is 0.006 meters cubed, divided by the constant, so 1.38 times 10 to the minus 23 meters squared kilograms second to the power minus 2 Kelvin to the power minus 1. And the temperature, which is 310 Kelvin. So Kelvin cancels. You don't always have to do this with the units, but I do advise you to. So meters cubed cancel with meters squared. So Pascal is Newton per meter squared, which is kilogram meter per second squared per meter squared. So meter, so it's kilogram second minus 1, meter minus 1. So kilogram and kilogram cancels. Meter to the power minus 1. Meter to the power minus 1 cancels the meter. Second to the power minus 2, second to the power minus 2, and second to the power minus 2 cancels, and we have no units. And that's what we want. All the units must cancel. So yeah, where's the Q&A? The Q&A. Why do we use the pressure of the CO2? Well, because we're interested in the amount of CO2 in your lungs. We're particularly interested in this gas. All right, so yes. Oh, sorry, yes, that's bad. That's the blackout. So it's 4,000, of course, 4,000 pascals, sorry. Partial pressure. So I tried to explain partial pressure a few minutes ago. Okay, let me finish this, and I'll try to say a few more words on partial pressure. But also, David is answering about partial pressure. So 4,000 times 0.006 divided by 1.38 times 10 to the negative 23 divided by 310, which is 5.6 times 10 to the 21 molecules. That's a lot. So that's in total. Per tree, we have the number of molecules divided by the number of trees, and that is 5.6 times 10 to the 21 divided by 3 times the trillion. The 3 trillion is 10 to the 12. Yes, 10 to the 12. And divided by 3 times 10 to the 12. Wow, that's a big number. 1.18787000000 molecules per tree. So for every tree in the world, with every deep breath you take, you provide 1.8 billion carbon atoms or carbon dioxide molecules. Well, carbon dioxide molecule contains 1 carbon atom. So you can safely say that every living tree in the world has carbon atoms that you have provided. And it's not an exaggeration, right? Any tree in the world that uh, you have has your carbon atoms inside it, which is quite cool. But yeah, actually, we haven't used the molar mass of carbon dioxide at all because we didn't need to. No. Okay, so there were two questions. Partial pressure is what I was trying to explain. So if you have two types of gas, each gas produces its own pressure. So for example, uh, I have 100 atoms of this gas and 100 atoms of this gas, and each of them provides half the pressure. Now, if I double the heavy particles, the heavy gas produces 2/3 of the pressure, of the total pressure. So partial pressure is a fraction of the total pressure. Does that make sense? Hopefully. Um, anyways, and how did the units cancel out? Well, I'm happy to walk you through that again. So we started off with, well, actually, we started off with pascals times cubic meters divided by meters squared, kilograms, second to the power -2, Kelvin -1, and then Kelvin. I'm missing, I skipped the numbers, okay? So Kelvin and Kelvin to the power 1, so Kelvin and Kelvin to the power -1, they cancel. Then meters cubed and meters squared cancel, and you're left with meters. And now pascals. And we know that Pascal is Newton per square meter. But Newton, the Newton, is kilogram meter per second to the power -2. So, and then we have meters per meter squared, kilogram, second -2, and then meter. Oh, that's second. Is that second to the power -2? Oh, per second squared. Sorry, there's no -2 here. Per second squared. So second squared and second -2 cancels. Kilogram cancels. Meter, meter, and meter square cancels, and where you're left with no units. And because we have the number of molecules is no units. Okay, so I really like this question because I like to think that every exhale I help trees grow. I don't know. Every tree except the tree in my room. Problem 6. An air bubble of radius 10 millimeters rises from the bottom of the lake depth. So this question is almost identical to the one in the assignment. So it would be a good start if you are struggling to know where to start. So you have a lake and there's an air bubble at the bottom. The radius of this bubble is 10 millimeters. And the depth of the lake is 5 meters. 5 meters, and that's h is the depth of the lake. The bubble rises, and as it rises, two things happening. First of all, the temperature is changing because at the bottom, the temperature is 6 degrees Celsius, and at the top, the temperature is 30 degrees Celsius. So the bubble gets bigger. Also, the water pressure becomes lower as we go up. The water doesn't squeeze the bubble that much, and the bubble expands even more. So there are two. Okay, sorry, I got a distraction here. Oh, no, 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 no. Oh, say hi. Okay, and now go. Apologies. The bubble gets bigger as it reaches the top, and the radius is question mark. Let's call it radius 1 and radius 2. So what laws can we use? Well, there are different approaches you could take. You could say that PV, because the number of atoms inside the bubble is fixed, right? We don't get any new atoms because if there's this much air, then well, that's the fixed number. That's the number of atoms of air. So it's N K times the temperature. But you can also divide both sides by T and say PV divided by T is NK, but the number of atoms is constant. K is constant, so that's constant. In other words, you could say that PV over T is constant, which we already know. So you could say that pressure at the bottom times the volume of the bubble at the bottom divided by the temperature of the bubble at the bottom is equal to the pressure of the pressure inside the bubble at the top, the volume of the bubble at the top divided by the temperature of the bubble at the top. Now we are interested in the radius, and we know that the volume of a bubble is 4/3 pi r cubed. So let's stick that in. So pressure at the bottom times 4/3 pi r1 cubed divided by T1 is equal to P2 4/3 pi r2 cubed divided by T2. 4/3 cancels, pi cancels, and size, when we say size, the radius, we mean the radius in this particular case. Usually by size we mean diameter, but we need the R2. So we multiply both sides by T2. We divide by P2. So we get R2, P1, R1 cubed multiplied by T2 divided by T1 multiplied by P2, and that's R2 cubed. And from here, R2 is the cube root of P1 R1 cubed T2 divided by T1 P2. Right. And now we need to work out the pressure, and we need to work out all the values. So we have these. And what do we know? We know that at the bottom, pressure, well, we don't know the pressure at the bottom yet. We know that the pressure at the top is atmospheric, right? This is the atmospheric pressure at the top. So it's the atmosphere, and the atmospheric pressure is 10 to the power 5 pascals. Now, R1 we know, which is well, we can actually do it in millimeters, right? It's 10 millimeters because the answer will be in millimeters. And then P R2 is question mark. T at the bottom. Well, it's 6 degrees Celsius, which is 279, 6 degrees. 6 degrees Celsius, which is 279 Kelvin. And temperature at the top is 30 degrees Celsius, which is 313. No, 303 Kelvin. Okay, and now we just substitute all the values. Oh, the pressure at the top, at the bottom. Pressure at the bottom is provided by the atmosphere plus pressure of the atmosphere plus the pressure of the water. Right? So you probably know that if we take that under pressure. So for example, let's say you are here and the atmospheric pressure is 100 kilopascals. It's 101 kilopascals, but it's approximately 100. But if you go into the water, like 1 meter into the water, the pressure increases. 2 meters, pressure increases. 3 meters, pressure increases. So above the water is 100,000 everywhere, right? But under the water, you have the additional pressure of the water. And it's the pressure of the air plus the pressure of the water. Pressure of the air is 10 to the 5 pascals. And the pressure of the water is rho GH, where it's the density of the water times the gravitational field times the height, the depth, which is density is 1,000 kilograms per cubic meter. Gravitational field is 10 newtons per kilogram. And the height, the depth is, what was the depth? Is 5 meters. 5 meters. So that's 50,000 pascals. That's an additional 50,000 pascals. Right. So P1, that's going to be 150,000 pascals. That's the total pressure, where this is 100,000 pascals. So 5 meters in the water, the pressure is 1.5 times the atmospheric pressure, which is quite an important number. Now, finally, we can work out the radius of the bubble. It's cube root of P1, which is 150,000, multiplied by R1, which is 10 cubed, times T2, which is 303, divided by temperature 1 is 279 times P2, which is 10,000, 100,000. So we get cube root of 1.5 times 1,000 times 303 divided by 279. Where did I get the 10 to the power 3? Yes, divided by 1. 11.7. 11.8 millimeters. It's a little bit underwhelming, but